Okay, thank you. Thanks for coming. Whenever I speak at a conference, I always ask if I can speak on the last day directly after lunch. It's the best session. We're going to talk about Antifragile and how we design systems and how we need to change the way we think to design systems in the future. A little bit about me. I'm a founder at a company called Black Tulip Technology, and that company actually has a mission, and that mission is to take two contradictory ideas of how we build systems. One, which is complexity science, which says that we don't know anything, we can't predict the future, we're not in control. And the other being systems engineering, which says you'd better be in control or someone's going to fire you when this crashes and burns. And how do we get those two things to come together and actually produce something useful? My mission with the company is to forge those two ideas and present an alternative, a new way of doing architecture and designing systems. And so this talk today will be focused on how we can do that, the first tentative steps we need to take to be able to merge these two worlds, and as a result deliver systems that are more fit for purpose and have a better level of perceived quality. I've had a bunch of fancy titles which you can see up there. One of the things I'm most proud of is this fish, which is a Baltic sea trout, and these things are not easy to catch. And there's a whole other talk I could give on the relationship between complexity science and fishing, but that's for another day. So, this session, like I said, it's really important that we start to interface with this question. But it's just a taster, so I'm trying to squeeze a 4-day course into 45 minutes, so it might get a bit intense. It is potentially shocking when you start to look at the world through the lens of complexity. You start to realize that things aren't quite what they seemed. And it can be shocking for people who are attached to a certain idea, a certain way of thinking, or a certain way of doing things, a certain methodology or language or platform. And so there might be some instances where you feel hurt because I say we shouldn't really be doing that anymore. I apologize in advance. I have this. It might get a bit technical in places. I speak to a lot of enterprise architects, so I have to ease them into it. So complexity. How many of you in the room think that you know what could accurately define what complexity is? Okay, one guy. There we go. So complexity is actually very much misunderstood. When most people talk about complexity, especially when we talk about it, what we actually mean is really complicated. Even in the field of complexity science, if you read the literature there, you won't find two definitions of complexity that are like each other. They'll all talk about feedback loops and sensitivity to changes in inputs and nonlinear responses. But there's no generally accepted definition of complexity. The best definition of complexity I ever read was written by an Italian researcher on the web, and he said that complexity is anything where you're beyond the point that our science and our engineering can answer. If you don't know what's going on, if we don't have tools to control it or measure it, it's probably complex. And we, as software engineers, we need to be aware that the world is actually becoming much, much more complex because of what we did, right? We're making it easier for people to connect with each other. We're making it easier for businesses to connect with each other. And those interconnections increase the ripples through the system when things change, when we change the inputs. And that has real implications for us who are designing systems to support these interconnected businesses and interconnected societies and interconnected people. And all too often as engineers, when I talk about complexity, everyone zeroes in on what they're building right now, their solution and all the connections between the little components and what happens in my solution. Okay, our solutions aren't necessarily complex. They're generally very complicated. Sometimes they're complex. They can be complex, but that's a different talk. Most of our solutions are complicated. The thing that's changing is that our complicated solutions have to be able to respond to these huge bubbles of complexity that surround them. And the things that are inside that bubble are our teams, our corporate cultures, our businesses, the markets they work in, the industries they play in, the societies that they're a part of, the societies that they interact with. All of these things are constantly changing, constantly warping at ever greater speeds. And as they do that, they warp and bend and twist our solutions. And we have a word for that. We call it requirements churn. And that's our way of saying it's somebody else's fault, right? But it's not. It's the way the world is, and it's increasingly it's getting more like this, and it's getting more extreme. And we, as designers of software systems, have to be able to meet this in some way. And when we don't do this, right, we'll blame it on the user, but the user will blame it on us, and they'll say that this system is lacking in quality because something unexpected happened and the system fell over. And quality can be, there are lots of definitions for quality, even more probably than complexity, but quality is generally, can be expressed in how well we meet complexity. And in order to try and get a control on quality, we can engage in systems engineering, which covers the most common kind of faults that we'd expect to find in our system, which are the kind of faults you'll find in the middle of the bell curve. The ones we can expect, the ones that are predictable. What you'll find is, in my job, I do a lot of reviews of systems, especially systems that have crashed, haven't worked well. What you'll find is that most teams aren't even covering this middle part of the bell curve. And even when you do, when you've done your utmost, you'll still get hit by something called black swans. Things that you could never have predicted, things that no one could ever have predicted, things that you never thought of. And that's because of these interweaving complexities in the big bubble around our solution are crossing each other. There's many permutations, and they're delivering things that we had never expected, and they take the system out. What we need to do is to find some way to marry these two worlds together. The alternative is simply to give up. And I believe that we are on the cusp of a new evolution in software. And we've had this journey from procedural to modular through object orientation to service orientation, which gets a bad rap because of what the management consultants did to it. But if we look at service orientation in a positive light, and if you think of Jeff Bezos' memo to his programmers back in 2003, where he said, do it this way or you get fired. Service orientation turned a bookseller into the most powerful computing platform on the planet. Okay, there's some value in that. It also delivered cloud, microservices, and event sourcing are all products of service-oriented thinking. As our systems more and more become revenue critical and mission critical to companies operating in these complex, growing complex environments, we need to be able to meet that. And it's going to require a different type of system, and I'm calling this complex responsive systems. Not complex systems. Okay, we don't have to build complex systems, even though that's fun, and it's fun to model them and get into the math and all of that, where we can be comfortable as engineers. But these are systems that have the capacity to respond to the complexity around them. And when I say system, it doesn't just mean the code, it also means the team. Okay? So this isn't AI or magic code that responds to things it never thought of. It's some code and a team that can modify that code. And so we need to talk about how, in general, we as people meet complexity before we can take the next step. And there's a bunch of different ways that people meet complexity, and you'll recognize all of them when I tell you. The first way that we meet complexity is to ignore it. It's just like, it's not there, I don't care. Your eye takes in, I think, 10 billion points of data per second, the vast majority of which it just drops on the floor, and it sees what it wants to see. And when we're building software systems, we've all seen people behave like that, and we've all behaved like that ourselves. Another way to deal with complexity is through heuristic. Okay? We build up a set of responses to certain patterns that we know get us out of trouble. Now, we've all been living in cities for many, many generations. If you walk through the woods and you hear a rustle in the bushes, your limbic system goes into action, your legs stiffen, you're ready to run. That's a heuristic that keeps you alive. Okay? It's out of place, mostly out of place, because there aren't many tigers here in Amsterdam. But it's one way of dealing with complexity. And that's a good thing. Okay? It's a good thing to have a heuristic. That saved lives back in the day. It's a bad thing when we take a heuristic and we employ it where it's not, where it doesn't work anymore, because it's our only response. We're limited to that response. Another way is detailed in a really, really good book if you want an introduction to complexity, which is called Complexity and Organizational Reality by Ralph Stacey, where he talks about the dominant discourse of management. And the dominant discourse of management is where we say, we're in control, we're the leaders, we make a plan, the plan executes, and that's the way the world works. We decide. And then they get to the end of the line and their plan hasn't worked, and they look back over their shoulders and they say, well, that's what we meant. Okay? We were right anyway. And they construct a narrative around what happened and they say, we're in control. And they go to the next project and do exactly the same thing. That's one way to deal with complexity. It's almost the same as ignoring it, except you're giving yourself a pat in the back. And now nobody needs to do an MBA. Another way to deal with complexity is to just accept it, okay? And this can sometimes irritate me with some agile attitudes. Embrace change. It's like, I can't do anything. There's nothing I can do about it. It'll happen. We'll rebuild, okay? It can be a viable strategy in some cases, but it's not the strategy. Another way to deal with complexity, and everyone will recognize this, is to outsource it, make the problem someone else's, okay? So we're building a system, this little complicated system in this big complex bubble, and we don't want to deal with the big complex bubble, so we go up to our user and I say, tell me your requirements. I've just outsourced all the complexity on this guy who works for the business, so he's affected by the dominant discourse that Stacey talked about, so he can't lie. He can't say, oh, I don't know, it's a big complex bubble and everything changes. So he'll tell us something which can't ever be the truth. We go off and we build a complicated system. We come back, he says it doesn't work, and we say, well, that's your fault. That's one strategy to deal with requirements, and we've gotten very, very good at that. We have contracts, paperwork, templates to help us do this. The other way, which you'll all hopefully recognize again, is goats. Okay, it's one way to deal with complexity. Goats. Back in the day, when we lived in tribes, and we didn't have modern medicine, and we didn't understand how the human body worked, if a child got sick, we slaughtered a goat, okay, as a sacrifice to the gods, and we hoped the child would get better. And the thing is, not everyone who got sick died. In about 20% of cases, maybe the child got better, okay? So if your child got sick, you're going to slaughter a goat because the chances go from 0 to 20, right? And anyone who's done any work in modern software development will not find it too difficult to think of many examples of how we slaughter goats, okay? I'll not name the examples because I'm trying not to offend anyone. So, how do we deal with complexity as architects, as software engineers? The first thing we need to do is to understand that it's not about the application, it's not about the code, okay? If you want to take the step from being an engineer to being an architect, if you want to be able to have some impact on the complexity around you, it's not about patterns, it's not about software, it's not about clean code, and it's not about deployment or continuous integration. All of those things are useful, but they're just examples of complexity themselves. It's about the context. We have to understand the context. And when we try to understand the context as engineers, we're moving from a world where we're in control, where we decide when we press F5 or whatever you press to compile in other universes. We are in control. And moving into this means accepting that we're not in control anymore. You're going to have to interface with something that isn't a machine. It's a big bubble, and it's full of horrible things called people. who change their minds and join together in different unions and do inexplicable things and can't be compiled. Right? There's no set of unit tests you can write to make them behave. It all gets messy and yucky and horrible. And we all come from this culture and we have this culture in our industry, and we know that we have it, and it's damaging, where we all think we're Chuck Norris, right? And you've seen these action movies from the 80s where the hero goes into a bar, right, where everything's inexplicably made of wood from IKEA. And there's like 500 bad guys and they all come running at him, and he's just like, yeah. And people go flying, and he leaves the bar, straightens his jacket, not a scratch on him, okay? In our industries, there's this attitude that we have to be Chuck Norris all the time. So if I pick anyone out of the crowd and I say, do you know what model-driven development is? They go, yeah, sure. And they look it up on Wikipedia. You know it, right? we can never say, I don't know, we don't know what's going on, this is fuzzy, this is weird. Okay, it's really, really difficult for us as engineers, and we have to take that step back. And if we don't change the way we look at the world, then we can't change the way we interface with the world. And if we don't change the way we interface with the world, we're going to have systems that we continually deliver into complex environments that just collapse. So, how do we meet complexity? How do we interface with it? What do we need to do? Which three-letter acronym? No, okay. So this guy, Nassim Taleb, wrote a book about 10 years or so ago called Antifragile, which caught a lot of people's imagination. It also irritated a lot of people. A lot of people are unhappy about the way he wrote the book, or his tone, or the term antifragile itself. There's a whole chapter about why you shouldn't trust us geeks, but you know, we need to choose to not take that personally. The thing that he actually did was he made complexity accessible for everyone. He wrote a book that's easy to read, that's entertaining, and he made the core concepts of complexity accessible. And he talked about the idea of a system being anti-fragile. And the reason I'm bringing that up here is because an anti-fragile system, in the way he describes it, is the perfect metaphor for a system that successfully meets complexity. Okay, that's what we're trying to do. We're not trying to build invincible things, because anti-fragile doesn't mean invincible. We're trying to build a system that can successfully meet complexity. And an example of this is the human race. So in the 13th century, the Black Plague came to Europe, and it killed an awful lot of us. And you might think that makes us quite fragile. But only some of us died, not all of us. We're still here today, and probably, because we can never be definite in complexity science, probably no one in this room is ever going to die from the Black Plague, from the Black Death. So we survived, and we're stronger for it, and that's the definition of an anti-fragile system. Something that survives a stressor and comes back stronger. Okay? Don't get too hung up on the definition. It's a metaphor to bring us softly and gently into the world of complexity science. So, it's a very entertaining book, and one of the most important things that we're going to take from this book is the idea that an anti-fragile system's ability to interface with complexity is formed by exposure to stress. When we expose a system to stress, it starts on a journey from being fragile to being anti-fragile, or it dies. One of those two things, and all systems will die. Okay? Even an anti-fragile system will eventually die. Eventually we won't be here anymore. Eventually this planet won't be here anymore. You know, eventually, well, everything dies. So, it doesn't get any cheerier, sorry. So, Taleb's book is wonderfully entertaining, fantastic book, a great introduction to complexity, but it doesn't really tell us anything about how to build systems. There's a researcher in Norway, Kjell Hole, who took Taleb's idea and concept, and he wrote a book called Antifragile ICT Systems. Has anyone read it? Okay. It's free on the internet somewhere. And so he basically took the ideas and he analysed a number of IT systems, and he said, all of the IT systems that behave like antifragile systems have 4 properties in common. They have modularity, they have weak links, they have some level of redundancy, and they have diversity within their modularity. These 4 properties together give a system an optionality that make it more likely to respond to stressful situations in a way that allows it to survive in some form. And so he takes Taleb's sort of fluffy philosophy and turns it into a definition that we can relate to as engineers. Now, we're still not home yet, because all he does is describe it. He doesn't tell us how to get there. And that's the point of this talk. So we need to first understand what a stressor is. What causes stress on a system? So if I was to give you guys the job of building an aeroplane, being software engineers, you'd get all excited about the wires and the way they're connected and which modules it should be and what size of rivets are the best and how you draw your models and all those things that you all get excited about. The most important things when you're building an aeroplane are the things that stress the aeroplane, like air pressure, temperature, speed, vibration. You might have the best decomposition possible in order to enable reuse, but if it falls apart at a certain air pressure, nobody really cares, right? This has a direct relation to the fact that we build business systems, and business systems have their stressors, which we need to be aware of. Markets, currency fluctuations, competitor behavior, cultural changes, mergers and acquisitions, countries that for some reason want to leave the EU, despite not knowing what that means. Have to remember that there's a camera as well. Stressors are really, really important, and it's important for us to be able to talk about stressors in a way that actually relates to the market that we're operating in. Okay, so if you go to your management and you constantly tell them about how brilliant DDD is or why you need to do TDD, and they keep rejecting you and they keep saying, and you don't get any traction, is because they're interested in stressors. What's happening with the market? Why are we not selling this? Why are customers leaving us in droves? Okay, when you can relate your software design choices to the stress that the system is under, it becomes much more natural. That's a big step for a lot of engineers to take. And that's why some of this stuff is unpopular. But if you want to make the move to being an architect, you have to take this step. And we've been saying that for 10 years. And architecture hasn't really succeeded in grabbing that rose by the thorns, so we need to take another stab at it, and that's what this is about. So the process looks like this. You go into a room, you meet some business people, they tell you about their problem, you go straight to your heuristic, okay? It must be a tiger, okay? You're going to run. And so you say, well, while they're talking to you, you're already solving the problem. You're saying, well, there's a web layer, and there's a business logic layer, and there's a database, and you're not even really listening to them anymore. And you're thinking about components. And the way this process is going to work is that we're going to introduce stressors. Okay? So the first stressor I can think of, a competitor drops their price. Okay? How many of you can answer the question about what happens internally in your system when a competitor drops their price? Okay, that should scare you that no one knows that, because when a competitor drops your price, this business guy here that I was torturing earlier on comes running down the corridor with a whole bunch of mad requirements no one's ever heard of, you've never heard of, and you have to react to it in your system, and you don't know whether your system can react or whether your team can build it or how long it's going to take. Competitors drop their prices all the time. This isn't a surprise. Okay? We are too disconnected from the complex bubble that actually determines whether our systems succeed or not. So we apply the stressor at design time, and we say, if we want to cope with that stressor, we need to change the system a little bit. And so we change our decomposition. And we do that with the business. We say to them, what are you going to do if a competitor drops their price? And as soon as you ask them that, they're like, okay, the TDD guy is actually asking interesting questions that I can answer now. So they'll talk to you, which is a revelation. And we do this until we get bored. And we get a new decomposition, and the decomposition isn't based on the latest fad or the latest trend. It's based on the stress that we believe that our business can be exposed to. And we have a decomposition that's actually based on reality. And what happens is then we migrate from this, Because imagine if we put this in production and all these stressors started to happen. Then we end up patching everything on top of this, and that's how you get to your big ball of mud. To this. And then we do a little bit more work and we think, well, what if the data center burns down, so we got to do this. We got to have 2 of these running somewhere else. And we're not building anti-fragility, not yet, but we're moving away from fragility. The system is much less fragile to the stressors we know about than it was. And the first concrete step we do in order to make this happen is the stressor analysis. So what can change is more important than requirements. As architects, we're responsible for the behavior of the system, not the functionality. Your system will always die. Volatility is always going to destroy it. The only thing we're trying to do is affect the rate of entropy. We want our systems to die further into the future than they would if we didn't do this exercise. And so the stressor analysis is super simple. Super simple. You can even do it with managers. We take a spreadsheet and we record all the stressors that we can think of. And as a source to this, I use something called a business model canvas, which is a way of modeling how money and products and things flow through a company. It helps us understand what actually happens in our business. And we look at that and we come up with things that would hurt the business. A supplier goes out of business. There's an embargo between the country that we're in and a supplier or a customer is in. Our channel gets disrupted. A new competitor appears with a slightly different business model. And we ask the business, how do you cope with this? What are you going to do if this happens? And the business, of course, will always have a plan because they're trapped in the dominant discourse, and they'll tell you about it. And then you understand what the business mitigation is. Once you understand the business mitigation, you look at the solution you're thinking of and say, how much effort or energy will it take me to get from where I am today to be able to cope with this mitigation if it happens? Can I do it now at no expense while I'm still designing? Or is it something I can leave until later and have my team quickly implement if this stressor becomes actualized in the system? And if you stop here and that's all you do, you're already building better systems. And that's true for every step of this process, and I'm going to show you. There's an example, super simple. What does it impact our ability to do? How do we detect it? How do we mitigate it on a business level? How do we mitigate that on a technical level? And then we get to the fun part. And this is where we start to get closer to the engineering stuff and everyone gets more comfortable again with, oh, we can do this. But if we do this without doing the first part, it doesn't make so much sense. So how do we express our response to complexity in terms of modularity and weak links? So Hole said that all anti-fragile systems have a degree of modularity and weak links, which we call loose coupling, right? Weak links. But all systems that we build today have some degree of modularity and weak links, right? So the presence of modularity and weak links doesn't solve the problem, right? There's different levels of modularity. And so there's a guy called David Parnas. Oh, the guy getting really excited here. There's a guy called David Parnas who wrote a paper in 1972, right? None of this stuff is new. We've known how to do this for years, right? But remember that thing I said about we get 10 billion data points a second and we just drop most of it on the floor? Right? This guy wrote a paper called On Decomposing a System into Modules in 1972 and nobody read it. And he was completely right. And that's a shame. Anyway, and I've tested this. Now, this is DDD Europe, and you're all super smart developers, so you won't fall for this. But I do this all the time with developers. I say to them, I have a business process. It looks like this. A, then B, then C, then D. What's your decomposition? Right? What's the answer? Component A, component B, component C, component D. Now, this has some problems because if something goes wrong or there's a change in component B, we're going to hit A and C as well. Okay, this is basic service orientation, so it might be repetitive, but we need to drill this home. It gets worse because we have another business process that goes D, E, F, G. And what does our hero, the developer, say? That's D, E, F, G. But it gets worse because we have this infantile obsession with reuse. And the developer goes, hey, I can make this really elegant because A and D are kind of similar, and B and E are kind of similar, and we get this, right? And we're marching towards the big ball of mud here. And then a stressor comes along, boom, and it hits component D. And now B and D and A and C and F and their corresponding steps in the business process are all getting hit. And that developer thinks, if I'd been at university, I would have got an A on this paper because reuse and elegance, right? It's really scary. So how do we get around this? First thing we do is we decompose by flow, not by activity. Okay, so we break our solution, our business processes down into flow, information flow from one person or organization to another person or organization. No computers, no bits, no bytes, flows of information. And this is taken from a guy called John Snedden, who did this with the public sector stuff in the UK in the 60s. You notice a trend here, 1972, 1960. We already knew all this. Nothing is new. We take each flow, and by the way, we make these lines around each flow, we make these lines impermeable. Nothing crosses the line, ever. Okay? On a Bezos, you will be fired level. Nothing crosses this line. Until later on when we break all our own rules, but that's complexity. Right? So we take our flow and we decompose it into components. And the bit that's kind of shocking here is that when I teach this, and we have longer to do it, we do it randomly. Okay? We don't follow any rules, no axioms, no methods. Random decomposition. Why? Because you're going to give this to a developer or a junior architect, and their efforts are as good as random. So if we can cope with that from the offset, we're going to be okay. All right. Then we go crazy. No component is allowed to talk directly to any other component. They're only allowed to communicate via queues. And we give every component a queue in and a queue out in order to be able to talk to each other. That might seem radical, but if we go back to 1973, there's a paper by a guy who I think was called Hewitt on the actor model, and he said the same thing, and everyone thinks that's clever. So, another rule, no databases. If you want the database, you take a subscription on a queue, and you fill your database from there, and we separate reporting from process execution completely. If we have another supporting process where we add bikes to our catalog, and we're dependent on data, we take a subscription on one of their in or out queues and fill a little database that we keep locally. It's fairly standard stuff these days, right? Well, I wrote all this down 10 years ago, and I didn't dare talk about it because it just seemed so Star Trek compared to what we were doing then. But you know, the guys at LinkedIn were doing similar things, and Kafka came out of these kind of patterns. It's not that controversial anymore, so it's safe to talk about without, you know, getting destroyed on the blogosphere. But the thing is that we're not going to actually build this. This is an engineering exercise. We're not going to build it. What we have now is a solution with an extreme degree of modularity and an extreme degree of weak linkage, and that's good. But it's also expensive, difficult, and kind of nasty to work with in places. So what we're going to do is something that's called pulling the shoestring. And we go back to our design, and we go back to our list of stressors, and we say, when a stressor acts, does it hit this flow? If it hits this flow, does it hit, which components does it hit? And we start to look at which components get hit by the same stressors. We move those together, and we take the queues away. The queue's not helping us if they always get hit at the same time. And we'll look at that method in a little bit more detail. And you can end up with this. 2 objects in a database. Okay? And that's not wrong because you've used the stressors, you've used the complex environment around your application to determine that this solution will survive the stress that we see in the system. And that's okay. At least you got there by some form of logical decision making. As an architect, your job is to make decisions about a system. And now your decisions have a good ground. They're based on something rather than hunches and blogs and trends and products. You can make it even simpler and just have one object and say, well, a big ball of mud is the right solution in this particular case. Sometimes it can be. And what we're actually doing is, in philosophical terms, called via negativa. where the idea is that it's much easier to define something by what it is not than to define something by what it actually is. And Taleb talks about this as a way to get towards antifragility. We start off with a really big system that can solve any possible problem because it's so loosely coupled and weakly linked, and we strip it down to what we actually need. And after that, we go into something called Stressor-Flow component analysis, where we bring in now we're bringing in systems engineering techniques. We're stepping away from complexity. We've decided what we're going to do. We've decided how to reduce this complex bubble into a complicated decomposition. And we do a number of things. We use something called the design structure matrix, which is what real engineers use, which they teach at MIT to make decisions about dependency and modularization in airplanes and things like that, to decide which flows are coupled to which other flows, which flows have we made a mistake where it should be 5 flows, which 5 flows should actually be 1, and we change the shape of our flows based on that. And then we look at something which I call the Parnas counting. We take our components and we put a stressor over the whole system. And if a stressor hits a large number of components, we change our decomposition so that number comes down, so that when a stressor acts on a system, we're hitting less components. And what actually happens is the system starts to change shape. And this is why it can be completely random, because as you put the stressors over it, the stressors pull the form together. And you have a system that's capable of coping with its stressors and it's decomposed just to do that. And it's numerical. Okay? It's easy. You put numbers in a spreadsheet, and people understand it. 2 is bigger than 1. It's not that difficult. And what you find with a lot of decomposition methods is that you need some sort of secret sauce or some sort of secret understanding to be able to use them. This is simple, easy to do. And so this is an example from a real life project that I did in the United States, and you can see you get very, very quickly down to an actual decomposition, an actual system design. But it's justified and it will react to the stressors that we expect on that system. But we're dealing with complexity, so even though we're really proud of our stressor list and our decomposition, the one thing that's always true is that we're wrong. Because we can't predict the future, we can't know things that we don't know. There are things we don't know that are going to hurt this system. So what do? Well, this is where we have to really, really be certain that we're not Chuck Norris. And we take our architecture and we put it out there. We go to the business, we go to other architects. I always find an architect who's better than you and say, I put this together, can you find some holes in it? We've made decisions. When you're doing these stressor component analyses, you've got numbers that go up while other ones go down. And you've got to make trade-offs. You've got to make decisions. What's more important to this business? The ability to recover from an earthquake or the ability to recover from a drop in the value of the dollar or the euro? Where should we put our effort? And you bring people in and ask them that question. Now, there's different ways to do trade-offs. If you're a hardcore engineer, there are things like multiple attribute utility, where you balance, very scientifically balance 2 aspects of a system against each other, or multiple aspects of a system against each other, and come out with numbers. In the middle, we have something called ATAM, the Architecture Trade-Off and Analysis Method from the Software Engineering Institute at Carnegie Mellon. And that's a workshop methodology for getting the business and IT into a room together to discuss what are the risks, what are the stressors. This gives you a feedback on your picture of the world, and it helps you to question your own view, because none of us can ever be right in a complex system. And so the more intelligence we have, human intelligence, the better. At the far end of the scale, you have the stuff that Cognitive Edge are doing with SenseMaker. Okay? How to grasp sense of a situation based on narrative by speaking to people and understanding the impact of culture. Which is called the anthro-complexity, which is another way to gather these weird fuzzy requirements. But always have this step, always ask yourself, why am I wrong? Because you are wrong, and if you accept that, it's easier to ask the question, why am I wrong? And once you've done this, you've got to go back and think about your stressors. Did we do this right? Is our decomposition responding to these other complex elements like the business and people's opinions and our culture. Did we get that right? Do we have to tweak anything? And then we get into the really fun bit where all the engineers go, ooh, okay? This is failure mode effects analysis. So we've broken our architecture down into a series of flows, remember? And each of those flows has a number of components in it. And failure mode effects analysis is stolen from Six Sigma, and this is systems engineering. So we're getting more and more confident in our decomposition and our understanding of complexity, and we're starting to do real systems engineering. If you leave this room and only do one thing and forget everything else I've said, and you just do this on your projects, the lift in quality across, with this many people, all of Europe, will be fantastic. Unfortunately, this is also the bit that people do focus on because it's really engineering centric. The real power is in getting this to join up with all the other pieces. When we do this, we take one component and we imagine that it fails. And every component, this is a queue, has a number of failure modes. So a queue has a number of failure modes, like it can crash, the server that it's on can crash, the queue can get full, it can get slow, poison messages, things like that. There's a bunch of failure modes that this thing can do. And so we write down in another tab in the same spreadsheet, so we only need one tool so far, so we're not trying to sell anything. We write down the impact on the system, what happens in the system, and we also write down the higher level impact so that we understand what's going to happen above this level, what will be the implication of this actually going down on the business so that we don't miss something really important. And we write down detection, which is absolutely vital. How do we detect it? How do we know when this goes wrong? And I always give my teams the same requirement. And it's not possible to reach, but I give it to them anyway, because just trying to get there is good. I say I want 0 seconds detection on all failures. I don't want people rooting around in this system going, why did this stop working? I want a message. You know, I want the team woken up out of bed, get to work, okay? And then we write down the mitigation. Again, mitigation. How do we fix this? And we get a list of mitigations. Now you'll notice something funny in both of these lists. When you're doing your stressors and you're writing up your business mitigations and your technical mitigations, I said we do it until we get bored. You'll get bored because as you move down the list, it gets repetitive. You realize that you've already mitigated certain things. When you do this, you'll notice the same thing. For many failure modes, you'll already have mitigated them further up the list. It's hard to get past 50. Depending on how big your system is, whoever left there probably has a bigger system. And then we can go back and do this with multiple failures at the same time, if it's really critical. And what comes out of this is something which we call non-linear system responsiveness. So if we solve for one stressor or one failure condition, then we solve for many. And what I usually teach, and it sounds like a joke, but it sort of is to not get hung up on probability, right? Because then you're bringing your own bias into things, and we're not actually as good at probability as we think we are. We can't predict the future, so there's no point in putting numbers on our lack of ability to predict. Let's say the first stressor I pick is lizards, right? It's always lizards. So lizards come up out of the sea and they destroy Amsterdam, and they set everything on fire because they're fire-breathing lizards, right? Everything's gone. So you've got some stressors. One, nobody's buying our product in Amsterdam today. How does that affect the system? Two, our data center was in Amsterdam. How does that affect the system? And then you build in mitigations, business and technical, that'll turn up in your stressor list and in your FMEA list. And you solve for lizards. And that sounds ridiculous. But I've solved for lizards. I've also solved for flooding in Amsterdam, which is much more likely, so I've heard. I've also solved for social unrest in Amsterdam. I've solved for power grid failure in Amsterdam. All of these things. So I've done these small steps for lizards, which probably don't even exist. Remember, probably, because this is complexity. This means that as we add more points to the system, as we cope with more stressors, it becomes able to cope with more and more stressors, more and more. It's more and more responsive to its environment. It's responsive to the complex environment. Now, Is it anti-fragile? Probably not at this stage. But the thing is that anti-fragile systems do exist. Microsoft Azure, Amazon Web Services are two examples of anti-fragile systems. So, anti-fragile is not perfect. It doesn't mean that it's invulnerable. It means that if someone should forget to renew a certificate and the whole system goes down, you're not thinking of any platform in particular, then that happens. The system goes down for a bit. The engineers rush in, figure it out, and what are the chances of that system going down again for the same problem? They're less. They're not zero, right? We don't make promises. And so the system now is loosely coupled. It responds well to stressors. What we've actually given it is optionality. We've given it a greater number of dispositions. It can shift and change, and it can exist in a multitude of different ways because we have this optionality, because we have focused modularity and weak linkage. And when a system has more dispositions, like the human race in the face of the plague, it's more likely to survive stress that it's never seen before. More likely. To actually get to antifragility means you have to take your job as an architect seriously. That means that you have to be there while it's delivered, and you have to be there after it's delivered and make sure these feedback processes actually feed into the system. And so just from thinking about complexity, rather than running at things the way we normally do, we get to the point where we realize that DevOps isn't a trend, it's a requirement. It has to be done. And this means to do this, we need to change the way we look at the world a little bit. And we have to understand the difference between behavior and functionality and recognize as a senior engineer or an architect, system behavior should be more important to you than system functionality. Functionality is always important, but behavior is what we should be taking responsibility for. So that as architects, we actually deliver something of value. So I don't jump into a team of developers and start telling them how to deal with functionality. That's their job, leave them alone. Okay? We want to get away from the ivory tower of telling people what to do. And we want to help as architects. It means getting rid of a whole load of heuristics that are stuck in us. And 10 years of working with cloud, they are really stuck in us. Cost and consolidation. Okay? If you're still working as a cost center, your role is janitorial. That's not good. Reuse, really, we should be moving past that already. N-tier patterns we need to get rid of, they don't exist anymore. And data center thinking, we don't really have those anymore. So what's it like to work on an anti-fragile project? Well, it's really intensive work on possible futures. It means working with the business, because don't make them anti-fragile or working in this way. I'm asking you to expand your breadth as engineers out into the business and into the culture, and I want you to understand business and people and how things move. That doesn't make you an expert, and you don't have to be an expert. You're not Chuck Norris. You just have to interface with the business and the people and the culture in order to be able to grab what's important and how it's going to influence your system. A lot of design testing, FMEA work, which is very intensive and incredibly critical, and also incredibly sensitive. So from experience, don't bring the guy that designed the system in and run through FMEA with him, because he worked really hard on that design, and your 250-point list of why it's not going to work can hurt people's feelings. It also involves provoking failure as a learning mechanism, which can be difficult, and it's incredibly intensive the first few times you do this. It's actually calling for a new breed of architect. So the architect who draws lines and boxes, that's not going to work here. Ivory tower architecture will not help. It's not just about Scrum either, it's about actually owning the application's ability to respond to its complex environment. Owning it and saying, I'm the person that's responsible for the way this system is going to interact with the complex environment around it. Which means you need business understanding, not business expertise. There's a certain class of enterprise architects who will tell you that you need business expertise. And I usually say to them, if you're a business expert, go and do business, because I heard it's quite lucrative. It also requires technical expertise, which, believe it or not, is a problem for some architects. A focus on quality, and you also need to be prepared to learn again every single time. When you do this once, and you do it right, there's a tendency to lift up what you've done and carry it with you as your new heuristic. That's not going to work either because these systems are complex. That's going quick. So, in summary, if we focus on stressor analysis and flow-based decomposition, we get modularity and weak links, the system that can actually stand changes in volatility. With tools like ATAM and multi-attribute utility and sense making, we can identify the truth about the perception of system behavior in this complex bubble around it. And if we use FMEA, we can identify flaws in our own thinking architecturally. We can harden the system and identify opportunities for redundancy and diversity to make that even stronger. And that's everything from me. Some contact details. I'll be back in Amsterdam on the 4th of March for a 4-day workshop where we dive into this, and everyone gets to bring their own system to the workshop and leaves with a much better architecture than what they came with, or they get hired. You can reach out on LinkedIn, feel free to send me emails, any questions or thoughts. I'm especially interested in criticism because I need stressors, right, to make this better. And 4th of March Amsterdam, 18th of March Stockholm, and available for anyone if anyone wants me to come and talk to their company about this kind of thing. Oh, thank you. Thanks for listening.
Thank you, Barry, for an excellent talk. We have a couple of minutes for a Q&A. Does somebody have a question?
Where can we register for the workshop in Amsterdam?
Just send me an email.
Oh, okay.
Send me an email here. That's a good question.
You probably heard about Chaos Monkey and the approach that Netflix is taking.
Yes.
Basically creating your own technical stressor.
Yes.
Do you see something like that as useful, or could you elaborate on that?
Yeah, so chaos engineering, which the field is being called, is absolutely useful. It really helps you. And once you've done your design, once it's in production, it's really good to do that and be aware of your system's response to stressors, because otherwise it's theoretical. So the alternative to this approach is to put your system out there and wait for stressors to knock it down, and hope and then it will get stronger over time, but the system will probably be decommissioned before it gets anywhere near antifragility. So chaos engineering is absolutely vital. What you'll get out of these spreadsheets is the foundation that you'll need to do chaos engineering properly. If you take a course on chaos engineering, you'll see FMEA as one of the first things you do in order to understand technical stressors. The problem I see with chaos engineering is it gets the engineers all excited, and they think that that's how we build resiliency. And there is no chaos monkey that can go to your competitor and make them drop their prices to see what happens in your system. If there was, there would be a lot of money in that.
Okay, I guess this is it. Thank you. Give a warm applause to Barry.